So guys, this is the moment for Petabyte-Scale.
Again.
A round of applause, and please enjoy.
Thank you. So sorry for not standing. You see my excuse here, and it's probably one of the, not the shortest title you've seen today. We're going to talk about Postgres in HPC context, so high-performance computing for petabyte scale in variable stars classification. So this is a subject I've been associated with for quite a number of years. So a few words about me. I usually don't put it, but since we're at CERN, and I've been at CERN at some point, it's kind of ironic why I came here and why I stayed here. I came to CERN because at the time it was the biggest object-oriented database in the world. It was around 2001. Anybody heard about objectivity? Yeah, this is what I thought. 2 people, not bad. So this was the sole reason I came to Geneva to work at CERN in an ITDB group to deal with the biggest object-oriented database in the world. It was roughly 400 terabytes at the time. But ironic is that the first task, a main, serious task I was assigned to was the migration from objectivity to Oracle. And it took 3 months. It took a lot of sweat and tears, and we did it. At the time, it was the biggest data migration in the world, apparently. I'm not sure if it's true. Then I was associated with some other database activities, usually using Oracle. For 16 years now, I work for Gaia, which is one of the ESA missions. I'm going to talk about it. In Geneva, we have variable stars group. So we're looking for stars that are very peculiar, that show some kind of human-readable variability. And I'm leading the group for the last 10 years from the technical point of view. 5 years ago, I set up Sednai. Daniel with me will show the part of the work that we do there. It's kind of spin-off. I'm continuing with Gaia, but Sednai is one of the ways to leverage distributed Postgres that we use for Gaia and other scientific software and approaches for data science for open source community as well. Astronomy, so it's CERN, but astronomy is actually quite nice if it comes to the challenges in the data, in the scale of the data, in the complexity and scientific challenges. Gaia was the first big mission, so all of this is about sensor data, right? Gaia was one of the big missions. It was launched in 2014, but missions like this take 20, 30 years. And sadly, I can announce that 2 days ago, Gaia mission accomplished. It's live. It's still there in space. It's 1.1 million kilometers from here. But now we basically shutting it down and sending out to the outer space. It's a 1 petabyte mission, roughly. Depends how you count, but this is the scale. And then you have a number of other missions. So you might have heard about Euclid, that was launched 2 years ago. There is, of course, James Webb telescope, which, as you see, is not that big if you compare to the others. And then you have ground-based missions or surveys. And this is becoming very interesting. You see, you have missions that have potential to have 5 exabytes of the total data. And the list goes on. So CERN is not the only place. It's huge, but it's not the only place that does the huge data science now. Gaia story. So this is mission of superlatives. We sometimes in Europe shy about what we achieve. And Gaia is example we shouldn't. Gaia is example where Europe is really showing excellence in what we do. NASA tried to do similar mission. They failed. So Gaia is example of the astrometric mission. So normally the idea is that you want to create 3D map of our galaxy, but also in the time domain. So you watch the galaxy over time, you're gathering the data, you're trying to derive from this data some interesting stuff. But normally it's 3D with time, you could say, the map, from a number of instruments. Its most successful is astronomy mission to date. It's quite big. Ground segment is around 600 scientists. In something called DPAC, so consortium. After the data release 2 in 2018, our impact surpassed Hubble. So this is quite big. I don't know right now today because of James Webb, but we are top kind of influencers of the astronomy, observational astronomy. One of my tests for the large language models was tell me what's the biggest camera in space, CCD camera in space. Oh, it's Hubble. No, it's not Hubble. Hubble is much smaller. Gaia was the biggest CCD in space, camera in space. It's 1 gigapixel camera. So here you can see the view of Gaia. This is like 2-tone 8 meters diameter shield. There's many things I could talk about if it comes to engineering of the spacecraft itself. Let's have a look at a few facts. So here I put, like, in the beta advertisement, 4 things running at the same time. But the important part is here. For example, we see the scanning law. Scanning law is the way we observe the sky. So here you see the projection of the sky. And you can see the heat map that tells you how often we see a specific part of the sky. And what it shows first for first few days, then it accelerates. In every 6 months, it scans the sky. You see it has 2 telescopes. And so it does it many times because the whole mission was 10 years, nominal mission. And you can see that the data is not really uniformly distributed. So this already gives you the hint that the data that we deal with is not so simple, right? Here we see the CCD camera. So one transit of the star takes more or less 45 seconds. We have a number of kind of CCD detectors here for the radial velocity, for the very bright stars, but most of the stars go through the G detection, so CCDs that calculate the G band, so it's visible band, then you have red band and blue band. Also, there's so many things that are happening around Gaia that I cannot list them all. But one of our things is to also try to show that you don't need images, like from beautiful images from Hubble or from James Webb now, to appreciate the science, data science, and astronomy. And this is one of the examples. You show the creation of the HR diagram, so Hertzsprung-Russell diagram from the sample of the Gaia close stars, so stars that are close to us. By sorting, basically by the magnitude or by color here, so the temperature. Then you sort by the luminosity, so something brighter is going up, dimmer down. And then you get structure that nature gave us that kind of describes what stars are, what kind of types they are. This is what it becomes, you can see now. And a lot of science could be derived already from this by adding, for example, the time, because here we see the average luminosity of the stars. So if you add the time, you have very interesting information. So already I'm mentioning time, so we're dealing with time series. If you want to look closer about Gaia, there's ESA website. The few important facts. Data release 4 is coming to 2026, so for us this is actually operational time. Final data release is coming around 2030. This is with, as you see, 6 years after or 5 years after the mission finished. It sees up to 22 magnitude, which means few photons per second if you talk about fluxes. It's roughly 1% of stars in our galaxy and over 10 years, and this gives you more or less 2.7 billion stars. Some of them are spurious, so we can talk about 2 billion, 2.5 billion. And on average, we get 80 observations after this 5 years, the first for DR4, 2 times more for the DR5. For example, for DR4, we have 120 or 122 billion transits. This converts to 2 trillion CCD observations from 5 instruments, and this is to double after. One of the peculiarities of Gaia is that Java was chosen as the main language for the consortium 15 or 20 years ago. So this is unusual for HPC. This is also one of the challenges that we're trying to address, and Daniel is going to talk about it as well. And as I mentioned, we are Gaia Variable Stars SU7 unit, which is around 70 people out of the consortium. So what variability studies are? We can assume that 10–20%, depends how you look at it, of all stars are variables. And there are many types of variables. This is taxonomy tree. I'm not going to talk about this, but they are important for a number of reasons for the science, because you can derive the cosmic scale, so expansion of the universe. You can check galaxy morphology, astroseismology. You can check for gravitational waves using some signatures from this data. Star evolution, of course, cataclysmic variables, galaxy evolution, black holes detection. Recently, we published the closest black hole to the Earth ever found. And there is no equivalent mission for another 20–30 years. So this is something that we're trying to do the best, because we have the short processing window, and here where the Postgres comes in as well. And also, if you're interested, there is a citizen science project. It's called Gaia Vari. So if you want to help us to procure better machine learning classifiers, you can go there and classify stars. There's a tutorial and so on. Also to show you what's the scale of what we do. So here I show the Gaia releases, data releases of variable stars, and this is the previous, basically best of the astronomy. The biggest catalog of variable stars in 2017 was 1 million. And we gradually, with data releases, increased this number. The last data release 3 in 22, was 10 million variables. And now we're basically thinking about 100 to 200 million variables. So this changes completely how you treat the science, how you do the science. OK, so why Postgres? There was a very interesting discussion at some point when I came to CERN. There was objectivity for astronomy as well, and there was Jim Gray. Jim Gray is one of the big fathers of databases, relational databases, and there was kind of a duel between people using objectivity at the time and SQL Server. He was part of Microsoft developing SQL Server, and he was always winning. So for me, it was one of the revelations that algebraic approach to the data is actually better than something that seems much more natural, which is kind of graph, object-oriented, that you traverse data as it's naturally connected. And this fourth paradigm was basically saying that he was promoting, saying that all the data should be stored in one repository, close to the logic. So logic should be close to the data. And you should be able to replay the science. So when you publish something, you should be able to prove that you can do the same execution of the workflow with the data that you got to the public. One of the main reasons why we chose Postgres was that, OK, we knew we wanted fast lookups. Astronomers work, they have their favorite star. Some people work with the stars that they know for 20, 30 years, some prototypes. And they know they want to look for similar stars, for example, or for this specific star, they want to check what it is, what's the result for it. So we know we want to some millisecond access to the data. On the other hand, we have to do some kind of batch processing because we have these 2.5 billion stars and 12 billion time series that we have to process. So we have to combine both. And we have to allow visualization, exploratory science. And also, I mentioned we were on Java from the beginning, so we had to decide how to marry Java with the relational database. We bet on OpenJPA. This is one of these JPA's Java Persistence API from Java. It's kind of, I think, kind of died, but we're still using it as a patched version. But to get really the speed, we're using Copy API to ingest the data. And also, one of the good things about Postgres was that it had kind of traces from its original Ingress object-oriented database, kind of type system. One of our modules, which is responsible for the data ingestion, is, for example, capable of uploading the data around 13 terabytes per hour. So when we're talking about, for example, backups, we don't do backups because it's too much data. We know we can use our software to bring back at least the input because it's faster than actually the tools that Postgres provides. At the time, the main contender was MapReduce, so a few Citus was too immature, Greenplum was open source too late, and so on. So in principle, we bet, and we were quite happy. And there is short history how it happened. We start with the regular Postgres, 9.6. Then something interesting happened. I was looking for the solution which is horizontally scaling. This was Postgres-XC by Koichi Suzuki, who I think now is also part of EDB, right? We deployed a cluster of 4 nodes on this. Then there was problem with Postgres-XC involved into Postgres-XL. It was more about stability and number of improvements. We did actually data release on the first and the second. Using the Postgres-XC and Postgres-XL. And then we switched to T-Base, which is another fork of Postgres-XL, which is run by Tencent. And now we're thinking about actually pursuing, using some grants from European Commission and any collaborators that are willing to be with us to do this. We also so Daniel is going to talk about the Aero project that we're part of. So this is part of the European Processor Initiative to have processor skills and stack in Europe for the databases as well. And we're trying to enable GPU acceleration in the database on this. So the data model, few words on this. we're talking about partitioning and sharding when we're talking about horizontal scalability. So partitioning is very simple for us because we have very powerful construct which is called hillpix. So this is sky pixelization technique, simply. It's nested, so you see this picture here. Basically, you can nest it indefinitely. Usually you do this up to 12th, 13th level, and you have very small area covered. But it's super fast. So if you want to do some joins that are based on vicinity, it works well, and it's monotonic. So when you want to do something like range partitioning, you want something to be monotonic, of course, because you want to have control of the stuff to be clustered together. So this thing is, the hillpix ID is monotonic, and our source ID is based on this. And then we have input and output. And for output, we have runs. Runs is basically the concept of having configuration, software, and data. And we have run ID, and this is similar. We keep the source ID as the partitioning and sharding key, but we add it in the top as a partitioning key. In principle, we're storing and we're dealing with time series, right? So we store data in the Postgres arrays. We also using composite types quite a lot, arrays of composite types that have arrays of composite types inside and so on, as kind of, this is not typical, this is kind of input data that we have. And we also store some objects as blobs with user-defined functions using PL-Java or PL-Uni-Java that Daniel is going to mention to expose them via cast. So you can have some very complicated structures with custom serialization, and you can just expose them in SQL the normal way, let's say. And you can do indices on specific fields and so on. So this is what we are very happy about. So this is part of extensibility of Postgres that was also super important. Then we have the whole platform to process all this data. It's in-house made. It's similar to Think, I would say nowadays, with Slurm in batch mode. We have some visualization tools, so you can see the in-house made Vari dashboard. We store generic time series attributes. We derive them. Then we use the machine learning and dozens of algorithms to derive the results, basically our catalog of variable stars. And now estimated processing time for data is 4 on our relatively small cluster is 2-3 months. One of the heaviest parts is really looking for the periodicity. So it's kind of special Fourier transform that derives the period for you. And it's slow because you create here, you can show a bit of the frequency gram. From this data, you have basically like 500,000 or 1 million bins that you have to fill over many iterations. Also, what we're doing is a bit of hybrid approach. So we want logic in database using Java and R, and also GPU nowadays. But also we're doing the literate programming, Topcat. And also we have to remember that when we starting to introduce this new dimension of horizontal scale, you're adding additional problems because of the extra parallelization. So remember, we learned this also recently thanks to GPU effort. The A plus B is not B plus A when you're doing your thing in the database, especially if you're doing parallelization. So if you're doing data science and you want to be really sure your stuff is working, you have to make sure that your data is kind of fitting well within the number system or the type system that Postgres uses. Okay. So system architecture. So I'm going to talk about the Postgres, XL or T-base as we use it. The main part of the lure of this system is that it's basically looking like Postgres. You don't have to create an extension. Tables you can create. When you create a table, you just say it's replicated or sharded, or it could be default by as any, and can be a partitioned as in Postgres. Normally, it's based on Postgres. I mentioned before. I wrote before 10 or 12. There's some kind of cherry-picked selection from up to, I think, Postgres 12 or 13 maybe up to, but normally you can say it's Postgres 10. And at the heart of the whole thing is something called Global Transaction Manager. And this guy serves the basically transaction IDs. So this is your MVCC heart. So if this goes down, the whole system is dead. You can have the backup one, but this is how it kind of works. You don't think about it when using Postgres, but there's a special place in Postgres that gives you the transactional ID. So we have to centralize this. This is the only place that you have to centralize. The rest can be distributed. Then we have collocated on all the machines, here in this example, 3 machines here, coordinators and data nodes. Coordinators keep metadata. They are your endpoint to connect us to the database, and they are responsible for query or orchestration. And data nodes are basically storing the data, and they talk to one another to fulfill the queries. There are tools to manage the cluster. There's a number of extensions that are made especially for this horizontal forks. And there are a few caveats, like for example, the statistics are gathered per data node for your coordinator. So if you expect to see the estimates that are real life, you will not get it unless you want to wait a really long time in this special mode. Yeah, so this is, and here we have applications, and applications are regular applications. So in our case, this would be the both batch system, and ad hoc querying, some kind of research analysis of the input and the output results. For the hardware, we still keep the original setup with the 12 HP nodes, but right now we have the 6 Supermicro, basically EPIC, AMD EPIC machines with 1 terabyte of data, and hybrid storage, flash only nowadays, so it's NVMEs and SSDs. We have GPU per machine, so the idea is that we also want to create the algorithms that can exploit GPUs on this distributed setup, which is not that trivial. And it's on tuned Alma Linux and so on. Also, we tried a number of things if it comes to bare metal, like ZFS, and we failed. So I'm very happy to hear if anybody had a success story with a very performing ZFS on NVMEs, would be happy to hear. Also, XI rate, this was to another try to kind of utilize something else than the software rate for NVMEs for the database. So for the future, we want to do Postgres, basically want to expand Postgres to make it maybe closer to have possibility of Postgres extension. It's possible, but very hard, or we could say it's impossible unless you do some nasty tricks or patch a little bit at least the base Postgres. Because there's no parser hooks currently in Postgres, there's no main loop hooks. And yeah, Daniel is really trying hard to bypass this, but it's complicated. So it's a maybe longer thing to do. And of course, what I mentioned is enhancements of GPU usability on Postgres in general, but also in this context of the distributed setup. So I think we can start the Daniel part.
Hello, so I'm Daniel. For the remote persons, so my talk will be a bit more technical and deep and maybe interesting for some of the developers. So in case the remote persons have questions, feel free to send an email. I hope I don't get spam, but yeah, I'm happy to talk to people. Okay, so first, thanks to our sponsors, which are many. So it's the European Union, UK, and the Swiss. That's actually interesting. All the enemies. Anyway, so it's a different story. Anyway, so it's the Aero project. So what is the Aero project? So Aero project is like a sidekick of the European Processor Initiative. Since CERN, as we learned in the morning, is like a political bubble, I won't say anything about the political motivation behind, because that is a very strong kind of motivation. So I will just talk about, what it is about. So in the end, the goal is to essentially do a high-performance, power-efficient chip fully in Europe, at least the design. And it's a bit surprising that today we still haven't there is no European chip. But we are on the way. And the Aero project is essentially a sidekick to, if we have the chip, to make it actually usable, to make it cloud deployable, to integrate it into all the infrastructure, and to take all the performance out of it. Because the new chip designs, they have certain intrinsic new characteristics, like internal RISC cores or special HBM memory. So it needs a bit of fine-tuning of all your full kind of stack. So that's why we have this kind of big collaboration. So a lot of the collaborators are listed there. Probably a lot of the names you know. Yes? Sure. Sorry. Okay, thank you. Okay, probably it's now better. Great. Okay, so these are all our collaborators. Probably a lot of the names you know, some not. But for us, as Sednai, we are doing the kind of the pilot. And if you're interested in the details, so we have a very nice website. So we do a lot of also promotion. So you can look up on the objectives and also details about what all the kind of collaborators kind of are doing in our project. Yeah, the target platform is kind of from CPerl. It's a new ship. It's ARM based. We hope that we're getting access to it this year at some point to then essentially do the pilot on the ship and then test if all our kind of developments are properly working on the new ship and how much kind of efficiency we are getting out of the new hardware. Again, I invite you to visit the website of the producer, CPerl, to learn more details about their roadmap and their architecture. Okay, pilots. So I think Sednai is the leader, essentially the coordinator. And we have essentially 3 pilots. So one is from Pira Innovation, it's automotive. It's part of KTM. I think they do the kind of R&D of KTM. Here, I will only talk about these 2. That's essentially we are together because we are very closely kind of bound to the University of Geneva. So we do this essentially very intertwined. And this is essentially the high-performance algorithm for space exploration. So essentially the application, I mean, Christoph introduced you so nicely before. And then also more Postgres, why we are all here. How we can use Postgres on the new ships we are kind of in development in the European Union. And more general, how you can extend Postgres to use external accelerators. Yeah, so the core 3 kind of guiding points we have in the way how we are approaching this kind of plan or vision is essentially to move compute to data. That means essentially move compute into the database itself. And this means we need to have GPUs, or GPUs be able to be called from the database directly. And this is actually a highly non-trivial kind of operation. And one way we're doing this, because for us, Java is God-given, so we cannot question Java. It's a religion, so we cannot ask anything. So we have somehow to get Java to talk to the GPU. And that's why the collaboration with University of Manchester comes in, because they developed this kind of new intermediate layer, which is kind of called Tornado VM. Again, I invite you to look up. They also put a lot of effort into presenting their kind of software stack in a very nice and accessible way. And essentially, it's a plugin for your JVM, so a Java Virtual Machine, which allows you to, with a few kind of tags, automatically translate and parallelize your Java code, and then let it run on heterogeneous kind of hardware. So GPUs from all vendors, essentially, and even FPGAs. But how do we integrate Tornado VM into Postgres? Because the problem is, usually we have only one big GPU in each database server. Maybe if you're lucky and have a lot of money, you maybe have 2 or 3. But still, there's a competition, because the GPU has limited resources, in particular memory. And if you have, let's say, few thousand users on your database, I mean, you're very quickly running out of memory. So that is the case in Postgres and Java. So what is kind of very established is this kind of extension. It's called PL Java. It has been developed, I think, already for 10 years plus. It's very major. Maybe some people use it even extensively. It's very kind of solid. But it has, for our kind of applications, a certain problem. I mean, one problem is if you look, on the right, you have here like the schema, how it works. It's essentially all running in one process, in one user process. Now imagine you have a lot of users, or a user starts up a lot of background parallel workers. Each process will start up a virtual machine, which might be not so scalable in the end. Particularly if you just, you're starting, you're logging in, and then you just call one function, and you log out again. Well, one JVM called and one JVM terminated. And this for each user. And this makes it also then kind of difficult to control your hardware, your GPU memory. So there are some more kind of things which, not really a problem, but it's not so nice. For example, it's a very kind of old and extensive code base, so it's not too easy to kind of hack in it and introduce new features. For example, if you want to have native 2D arrays, it was actually not too easy to do, so I managed to do this. But yeah, it was a bit of effort. And then there's a trend, it's more like a philosophical, to move more and more of the code directly to Java. So if you do the create extension, well, first they start a JVM, and then they do a lot of stuff in the JVM just to create your extension. So philosophically, I'm not too happy about this. Yeah. So this, I think, kind of is one motivation. I mean, why it might be interesting to have a new Java handler in Postgres. And here I listed again, what is needed and what PLJava kind of offers and what not. Yeah. So that is our new kind of Java handler. It's a very early beta, so I just pushed it today to a bit more public kind of repository. It's a PL Uni Java, we call it now. It was a bit of a discussion how we in the end kind of call it because all the names are already taken, so namespace is very constrained. But the new thing is you can run it actually as a background worker. So what you see on the right, you have like the normal process where you can work. Usually you can start a JVM in the user process, but you can also start JVMs in an independent background worker. And there are actually two kinds. So it's essentially one I call global. By all users, they're sharing the same JVM, which gives you some restrictions because you cannot access via SPI then the data. Well, I would need to write my own SPI, but it's a different story. Or use this kind of thing I call background, where each user has an own background worker, and then you can also start multiple for one user. And there are currently kind of some kind of restrictions. Simply, because I didn't have time to really kind of implement all the features. So it's essentially like an early beta stage prototype. And if people are interested and want to collaborate on this, probably we would be happy to hear from you. Because if I do it alone, I can only do little things we need, but not really the full kind of story. But one kind of caveat, this is Java, so it's potentially dangerous if you don't know what you're doing, because we didn't code it in any security protections at all. So it's all on the Postgres level. So you need to know what you're doing if you're using it in production. Don't allow users to just create arbitrary Java functions, otherwise you're in problem. Some technicalities. So it's all JNA based, so Java native interface. So essentially most of the code is in C, and from C I start Java, and then do from C calling certain Java function and so on. And one interesting thing is, what's quite very novel is that I did this new, which I call nor JDBC interface. So usually in Java you use JDBC, it's this kind of standard to query your data. And this is something, it's new. It uses actually direct native memory access. And so this actually requires kind of Java 21. Some more restrictions. So you need to reserve kind of memory, because for the inter-process communication, you need shared memory. Because you have like two processes you need to communicate, and you can only do this via shared memory. So if you then send something to the background worker, all the stuff has to go through a queue, and then from the queue it gets kind of distributed through the background workers. And you need to reserve memory in this up to Postgres 17, before you even start Postgres. But in 17, there's this kind of new API, but I haven't implemented this yet. But it's definitely on the plan to look into at some point to make it a bit more easy to use. Performance. So all the numbers you see here is not the original PLJava, because I heavily hacked it to use native arrays. So if you would use the original PLJava, you wouldn't get this good numbers. Anyway, so with the very good numbers, if you use a background worker, the performance loss due to the going through the shared memory is relatively minimal. So there are like 3 different kind of platforms I tested on. There are some kind of strange things, and this is probably due to the kind of the storage, because the storage is different, and then your Postgres will take different kind of plans, and this is very hard to control if you have not the same hardware in the end. And interesting is what we had access for the NVIDIA Grasshopper. Because this is kind of the new kind of NVIDIA combined ARM chip with GPUs all on the same, essentially very close to each other, and with the kind of shared memory. So background worker now real performance loss. But the interesting thing is, if you now use my new kind of API to directly access Postgres arrays via native memory access, and there you see that you're actually getting a quite strong performance improvement. So you have the blocks you see like with GPU and without GPU. GPU itself doesn't give you so much kind of performance improvement because the unsupervised learning algorithm I tested it on here is not so much compute constrained. So that's why you don't get so big kind of performance gain. But you see that changing to the new kind of memory API definitely makes a big difference. And in the future, what we're planning is to directly shift the memory from Postgres to the GPU. But this is in the making. Yes, good. Yeah, very quick usage example. So it's very easy. So you just write your Java function. You can do complex types. You define a complex type. And then for a set of return, just return the array list. Done. Yeah. And when you run it in Java and you create the function, so only thing what is a bit kind of inconvenient is at the moment you still have essentially to specify, specify here the method, or sorry, the class name and then the method name. And then for certain types, you need to specify the signature of the thing because you don't have a direct one-to-one translation between the Postgres type and the Java kind of type. But yeah, so it's relatively simple to use. But of course, if you have the effort and time, one could make this more kind of comfortable to use, and it's still the advantage of PL Java because they have a lot of kind of machinery around to make it very comfortable to use. Yeah, one kind of thing. So this is still the kind of the code name everywhere. So it will be refactored at some point to this kind of PL Uni Java. So don't be surprised in a few years if you type this in and it doesn't run. Look at the README on the GitHub because it will be a bit different. Okay, so this was one part, and now let me maybe tell you another thing, which goes more into this direction of really going GPU computation in the database itself. So this is very multifaceted. So there are many different things one could do, but they're all quite difficult to do. One easy thing, I mean, at least for me, it was very easy to do. I will present here, and this might be actually quite interesting for some people. Yeah, and that is essentially a hack of the very kind of popular PG vector kind of extension, which we heard already some time today here, to run fully on the GPU. Fully mean I implemented only the Euclidean metric, but one can do the rest as well if one puts in the effort to generalize what I did. And again, warning, this will be more technical. Okay, so what is GPU-accelerated vector search? So for many problems, I mean, you need vector search or nearest neighbor kind of search. And for example, for us, we wanted to do really unsupervised learning on this very, very large scale data. And where you get into the problem, because for this kind of classical algorithms like KNN, DB scan, you would really need to scan over all points. And then, cold correcting all the distances. So it doesn't really scale very well. But how can we do this? How can we scale? And then there was this kind of nice invention of this approximate kind of nearest neighbor search. And there are many I don't know, 2 or 3 flavors of this, but most kind of simple is this IVFF flat. And the nice thing about this one is it's easy to understand, very easy to understand, and also it's easy to do in a distributed fashion. So if you have several kind of compute nodes, it's very easy to do distribute. So I used right side, just illustration data, 2-dimensional, your data set, and you have some kind of whatever kind of distribution. And what it just does, it clusters your data. So it just takes k-means, you cluster the data, and then you index your data by essentially the closest centroid. And then you just query essentially the closest kind of cluster. So when you compare just the distance with the query point, you just compare against each C kind of members in the little cluster there, or when you take maybe the 2 closest or the 3 closest. So you're getting sort of a recall performance kind of trade-off. Yeah, because you only have then to essentially calculating the distances for this little subset of the data, depending on how many centroids you just say to probe into. Okay, so most well-known, I think, is the PG vector, but offers you this HNSW, I don't say anything to this here, and the IVV flat. They implemented beautifully like operators, many metrics, and I think it's very nice to use. But there's one kind of problem with it, which I noticed. And the problem is what we need essentially to retrieve all the points at a certain distance from a query point. Yeah. And if you look into PG vector, at least up to I just looked now, January 2025, it really requires you to have a work clause plus an order by, and then they say there's somewhere also you need a limit, but I think you don't need the limit actually. You only need the limit for performance, but we cannot use a limit because we want to have all points. So what we do? Let me see. Okay, so there's another kind of thing. So you cannot kind of supply pre-computed centroids to PG vector, which is also not optimal for us because we can very easily pre-compute in our k-means on huge data sets distributed. Isn't what I showed you before in this kind of little performance kind of plots. So I also did this little hack. You can just in the little kind of modification I did, you can just insert arbitrary vectors, and that's your index. So you will then compute with arbitrary externally computed centroids your index. Okay, performance. So this is the flame graph of a very simple kind of toy data set because I run it on my notebook with essentially 3 XCXL nodes. On little GPU, the notebook kind of GPU. And what you see here is actually for this kind of thing that you want to get all points at a certain distance, he spends an awful amount of time in the tuple sort of Postgres. Look here, the read buffers here. Now the read buffers here. Where is it? See here, this is actually where you're reading now from the disk. This is my kind of split with my CUDA kind of code. But here, all this here is just sorting. Just sorting your data in Postgres. And if you look a bit deeper into the code, so this is like also essentially from now the kind of part of the PG vector code, where they essentially reading the buffers and putting everything in tuple sort. What you see there is they take all the probes you have, they take all the points in the probes, they sort them, and then it gets fed into the work clause essentially. So it all gets into the database stream, and effectively you're also then calculating twice the distance metric. Because for the sorting you calculate it, and then for the filter for the work clause you also kind of calculate it again. But little kind of hack. What happens if I just remove Postgres, just back and Q-sort? Well, it's actually quite better. If you look here at this distance, the time spent here is much bigger than the time spent here. But this might get you into trouble. If you do this in production, don't do this. You can ask me later in private why not, but yeah. Better is this one. So what I did is I introduced essentially a hack where I hacked the where clause directly into the order by clause. It's actually very funny. So maybe if someone is very involved in Postgres, can tell me actually if it's possible somehow to get via the standard Postgres API the work clause into an index scan. So I looked and I tried to I definitely spent a few hours in the code and I did not see a way to do this. So that's why I was forced to invent essentially a new operator, which I call like exclamation mark, and a new vector type, which I call vector advanced. And this kind of construction replaces you. So this is like a combined where and order by, because the vector advanced has 2 attributes. So it takes in another vector, which is essentially a query point, and an integer, which defines the operator you want to execute, and a float, which is the filter, so the where filter you want to kind of apply. So it's very basic. It's just a prototype essentially, but it kind of demonstrates you the machinery. So if you do this, suddenly all the stuff disappears, and you see actually that the buffer scan I/O is actually now the main kind of compute time stealer. That's what you want essentially. So good so far. Can we do more? Well, we can always do more. Well, not always, but often. Let's get us again off Postgres. So get rid of Postgres. So idea, so we have 6 A100 GPUs with 80 GB of memory. So that means we have essentially half a terabyte of additional memory. So why not use this to store completely the index? Because if you have 100-dimensional vectors of float 4, we can store 1 billion index points. Well, it's wonderful. So what do we need to do that? Well, first we need a Postgres background process, because we want to read the data or the index once and keep it forever in our memory. Well, forever means until essentially you kill the thing or you have some memory management running. And the added bonus is we can actually use the GPU to do the distance calculation and to do the filtering and to do the sorting. And this makes only sense to do here because we have the index already on the GPU memory. Otherwise, you wouldn't have this. The I/O transfer will kill you because the GPU needs to have something which is CPU bound and not memory bound. Okay, how do we do this kind of technically? Easy. So now this is a few lines. Postgres, wonderful API. So you can just, in a few lines of code, you kind of define a background worker and just tell here essentially the C function you want to call. And when you just hack into the PG vector, where we're getting the tuples, where you, now because you have, again, as in the Java case, you have to send all the data through shared memory to your background worker process, which now controls the GPU. And that is something like insertion like this. We have like a queue, and when you're putting it into the queue, and when the background worker gets a signal, and when the background worker reads it and does the stuff, and then it puts it back. And then this here load index essentially loads all the data if it's not loaded yet. And that is when in C++ and CUDA. Going from C to C++ is always nice to do. And then you just do the execute. It's again all C++ and CUDA. Okay, what performance do we get? So this is the without a background worker. So this is already the kind of by me tuned PG vector after warm up and so on. You need for this kind of search in this kind of 4 million kind of data set 260 milliseconds for a single query. If you now switch to the GPU worker, you're down to 17 milliseconds. And I think that is definitely a kind of impressive kind of improvement you can get. And how does it look in the flame graph? So this is the index cost for loading the index essentially from disk. So you do this once, and then you never see this again. And this one is the compute cost, so which is just what per query you're running. Yeah, so here you see at the bottom is the exec kind of thing. I had the exec query, and that's just all. So it's a big change. But of course, there are some kind of disclaimers, because we are forced to be in PG10 still. If you look on the GitHub link I gave there, you cannot easily run it in 17. You have to go back to 10, or you have to to hack it in by yourself. Another kind of things, I didn't implement any active memory management. So you load index the index, load index, and the memory is done, and then your worker crashes. Or if you want to free it, you have to kill the worker. But this is all kind of solvable problems if you have the time to implement the the boilerplate around. And of course, you have always to go to shared memory, so you need to reserve enough shared memory so that all the data you're sending in and out essentially gets through. And finally, so it depends a bit on the query how sparse the return is. In general, as more sparse the return is, as better will be the performance, because the filter will then filter out already everything essentially on the GPU level, and then only a little bit goes into the Postgres in the end, where you then does additional stuff in Postgres. Okay, can we do more? Well, of course, almost. So of course, minor improvements of GPU code. Doing good GPU code is an art in itself. So I don't claim that I'm a good GPU programmer. So definitely one can definitely improve on this. Something more interesting for me would be to look into NVIDIA GPU Direct, where you directly read from the NVMe drives via DMA. For this, probably I would need to re-implement the storage kind of full storage layer, but this would be fun to do. Otherwise, one needs to vectorize. So several kind of points in the same time into the GPU, because then you're getting one dimension more to scale, and this definitely gives you much more gain in the end. So there's definitely much more room to do here. Outlook, okay. So we're also working a bit on PG-Storm, so to port it to the distributed kind of Postgres. We have some progress there, but also there are some technical problems which we still don't fully understand. And one big problem we have is essentially that PG-Storm, they're very close to the mainstream Postgres. So we cannot really keep track with all the bug fixes we're doing. And that's why also one of the explanations why I did some preliminary effort to modernize XL, XC. And it was actually a major effort to do. But I was able, step by step, pushing actually XC first to 11. Pushing, I manually essentially took over the 800 modifications one by one, because you can only essentially debug the things if you really go feature by feature. So I was able to do it to 11 with 70 or 80% kind of coverage, and then I just went from there the normal kind of pull to 12, and I still have a 60% coverage there of the full regression test. So it's a kind of a way one could go, but it's a lot of effort to do, and I don't know if it's really worth the effort to do. But yeah, it's theoretically possible. Okay, so again, thanks to the sponsors and of course to all of you for your time. And do you have questions for me or Krzysztof? With the microphone as well.
Check. Okay. I forgot to mention one thing, very important thing. If you ask me, it's not because of snowboard or skis. This is because of CERN. I'm still a member of the CERN basketball club. And this, okay, so any questions? We know we just touched especially about Gaia, tip of the iceberg, but maybe.
Hi, so thanks for the nice talk, first of all. I would have a question regarding the indexes. So your index is made up of clusters, right?
Yes.
And how do you determine the number of these clusters and the properties?
This you have to set by hand. So in pgvector, you set by hand when you're generating the k-means. You set essentially the number of clusters.
Yes.
So there are some theoretical work how you can automatically define the number of clusters. For example, one method is called elbow method, but it's a bit kind of controversial. Mm-hmm. But yeah, there are heuristics how you could determine it, but pgvector doesn't do it, to my knowledge. So you have to by hand specify your clustering, and that defines you when you kind of recall kind of trade-off, performance trade-off.
So sorry?
And also, if you remember, we do kind of hybrid approach, because we roughly know how many types of classes or variable classes are there for this specific use case, right?
Yes.
So it's not very, very scientific from this perspective.
Yeah, but in general, I think the motivation of pgvector is, I think they kind of recommend to have this kind of square root kind of number of the data points. So they're really hardcore, just say cluster essentially like square root of n, your things, and then pick, how many kind of probes you want to have.
Okay.
But one could do smarter, there's definitely there are methods how one could determine, or one could even do other kind of clustering methods. But yes. I think the problem there is you see if you want to update the data, because if you do the updating the data, you have to update the index, and then you have to recompute.
Yes.
So so there are many ways and there are many solutions, but it depends on the use case in the end, what is good and what is bad.
Thanks. Yeah.
Any more questions? Or can we go on to the beer? Beer talk.
In principle, we are very open. If you're interested, just send us a message. We'll be happy to talk either about technical or scientific part. Thank you.
Okay, thank you very much, guys.